Quite an impressive background, Anatoly, and this is the presentation. Are you ready?
Thank you very much, Eli.
Please.
Thanks for the nice introduction. And yes, so today and hopefully tomorrow, we'll see many nice talk, but I noticed that many of them lack, or maybe not lack, but simply they use some certain hyperparameters without explicit explanation why this particular parameter was used. And we have a feeling that with more optimal hyperparameters, many of your work guys can boost in the accuracy. And this is why we would like to present you this work on the systematic search for optimal hyperparameters for the Tsetlin machine. And exactly the motivation for this works, all your presentation today, before that, and also the fact that it's widely accepted that for Tsetlin machine, you do need to set hyperparameters, and usually it's a manual research. Yeah. So usually you start with some research, trying different options, and after that you stick to some particular parameters. But the thing that these parameters that could be optimal for your particular case, for your Tsetlin machine, might not be universally optimal. So whenever you change number of clauses or other parameters, you might need to change hyperparameters. So this is one of the important motivation for our work. And of course, it's widely accepted that there is no such a model for hyperparameter optimization, which could be available for both Tsetlin machine and other machine learning techniques. Yes, there are some frameworks available, like Keras tuner or other tuners, but these frameworks are mostly based on some automated research. Maybe there are some variations, some randomization, but it's still a research, so it's still a brute force approach. So in our work, we wanted to explore whether we can equip other people with some automated or ideally automatic tool and models which allow you to set these hyperparameters in the optimal way without doing this random search. And of course, this is the hyperparameter optimization is only a part of a broader picture, sort of. So ideally and ultimately, what we want to do, we want to have a framework which would provide you an optimal Tsetlin machine architecture and optimal hyperparameters and an optimal hardware and software design for your specific task. So this is the broader picture, and the optimization of hyperparameters is important, but only a part of this idea. So I'll start with some brief discussion of the hyperparameters between and their difference between the DNN or deep neural networks and the Tsetlin machine, and then briefly discuss our research methodology, and finally, step by step, we'll try to cover all of the hyperparameters that you need to tune for the Tsetlin machine, and give you some tool that you can use to set the hyperparameters for your particular work. Right. So when you work with deep neural networks, artificial neural networks, the straightforwardly you need to specify the number of layers, the number of neurons, then some activation function, then you need to specify different algorithms and all the rest stuff. So quite a few parameters. And if you even look at the Keras API, so you can notice that when you compile your model, so when you create your model, so basically when you define the architecture, you need to specify sort of 8 hyperparameters. When you decide which optimizer to use, which is the algorithmic hyperparameters, you need to provide or set up to like 9, 13 hyperparameters more. And finally, when it comes to the training, it requires even more, 19 hyperparameters. So there are quite a few that you need to set. It is true that there are some of them, or many of them, have some default values. Yes, this is true, but still, a considerable number of them needs to be tuned or fine-tuned to achieve the best accuracy of the deep neural network. If you look at the right side, and if you compare the hyperparameters of the deep neural network and the Tsetlin machine, you can see that there are much favor them, or many. You can have only 5 of these hyperparameters. So the number of clauses, one of the most important, but basically it's limited by the available hardware resources. What are the most difficult to tune are the T and S, so the threshold, the voting threshold, and the sensitivity. And then there are some speculation about the number of state of the Tsetlin automaton and the number of training epoch. So in this talk, we are trying to answer and provide you also some insight into how to, is there some optimal for this or some of them of these hyperparameters? What is the interconnection between the different hyperparameters? Simply because if you change one, often it means that you need to change others. And simply whether we can predict or have some model which allow us to set up it in some automatic way. Right, so a briefly about our experimental methodology. So it's pretty simple. Well, so it's pretty straightforward. We are relying on the grid search, and the parameter of the grid search is here you can see on the bottom of the slide. So what is the steps and what is the variation of so the whole range of these hyperparameters. And so we done this extreme grid search. So it took us actually days and days and weeks, sometimes weeks. And then as a benchmark, we are using MNIST dataset. After each epoch, we logged the training accuracy and the duration of the training. And finally, once we collected all this huge amount of data, then we simply started to analyze it. And the results are quite promising. As an environment, we started using Google Colab. We found that it is quite useful, but it's still so the basic log performance. So you can pay more, but what you're getting in turn will last only for a few days. So we run our experiments for weeks. So it finally we switched to the high performance desktop, and then we finally continue all our results. We've done it multiple times, and we can see that the results. So we can see that the results are repeating itself. So what we are presenting now is repeated results which can be trusted. Right. So let's start with the most important, probably, or the most obvious question: what is the optimal number of clauses, and is there some optimal number of them? Apparently, if you fix T and S, so there is a certain optimum. So there is a certain optimum beyond which the accuracy starts to deteriorate. Yeah. So if you never change T and S, it means that you need to look at some particular number of clauses, and this could be the optimal number for that particular T and S. If you, however, what we can say is that well, the default assumption that the more clauses you have, the higher accuracy you can receive. It is true only if you are using the optimal TNS for that particular number of clauses. And if you look at the blue line at the very top, so you can see that it says that optimal TNS. So if you set the TNS optimally for the given number of clauses, you can always get the highest accuracy. But then you can notice that after the initial period of rapid growth, the accuracy starts to deteriorate. Well, it starts to, so the gain in accuracy becomes quite incremental, and at the end, it just stabilizes at some particular point. So the C is important, the number of clauses is important, but more important is to set the optimal TNS for that particular number of clauses. And of course, if you have more resources, so it's always beneficial. So there is no certain optimum. So this is the answer. There is no certain optimum for the number of clauses. The more is better. It is limited by the hardware resources, but you need to have optimal TNS, optimal for that particular number of clauses. So this is the answer for that particular question. And interestingly, if you look at this graph on the left, here you can see that this is a training time. So with a small number of clauses, you have considerable training time. And it's decreased until you increase the number of clauses up to around 50, and then you can experience a linear growth. So it means that from this point of view, there is some certain number of clauses which provide you sort of optimality from the point of view of the training time. Right. And the next step was searching for optimal TNS. And this seems to be quite useful and provide lots of useful insight into that. As I said, we've done a grid search, and then you can see on this graph sort of unfolded result of that grid search for a particular number of clauses. So for this example, it's 300 of clauses, and then we change the TNS starting from 5 to 50, and with a step of 5. So on the top, you have T, on the bottom is S. Yeah, so T is 5, S 5, 10, 15, until 50, and then T is 10. So it's a grid search. And here also you can see on the top, you can see that we logged accuracy after the first training epoch and the last training epoch. So for this particular experiment, we're using 100 training epoch. So here you can see that the difference in accuracy between the first and the last training epoch is changing. And if you select the TNS in the way that they are not optimal, apparently at some point you could see that they are swapped. So if they are not optimal, the more you train, the worse accuracy you receive. So it's interesting. And then if you look at the bottom graph, so this is a training time. Here also you can notice that there is a certain local optima for TNS. So for each T, you have some optimal S, and likewise for S, you have some local optima of T. And this local optima, apparently, it's also linked to the minimum training time. So it's crucial to select TNS not only because you want to achieve the highest accuracy, but because of the highest convergence. And the highest convergence means that you don't need to update your Tsetlin automata too often, and it saves your time and it saves your energy. So it's of particular importance. And apparently one of these local optima becomes the global one. So you can see that there is a global optima somewhere there for that particular number of clauses. And if you look at the 3D picture, so in the 3D picture, you could see that apparently it's sort of it's like a mountain sort of, and then on the top of this there is a peak, which gives you the global optimum out of all of that. On this slide, you can see how TNS depends on the number of clauses. So definitely there is a dependency between number of clauses and T, number of clauses S and S, and also you can say that T depend on S and vice versa. So what is interesting is that on the right side in the table, you could see the optimal setup for different clauses. Well, these numbers are quasi-optimal because we are using this the step of 5, but they give you an idea where is the optimal number lies in. And apparently you can see that if you have more clauses, you need to have higher T and higher S. However, it's not linear dependency. And on the next slide, I'll show you so what is a model you can use to approximate the optimal T and S. Right. So this probably is the core of our results. And here you can see that if you look at the threshold, the optimal threshold, it's approximate itself to the square root of the half of the clauses. So for example, if you are using 100 of clauses, so the optimal threshold would be, 200 of clauses, so the optimal threshold would be 10. Yeah, so it's a square root of the half of the clauses. And you can use, and this formula seems to be consistent across different data sets. So we were experimenting not only with digital MNIST, but we also used the fashion MNIST and the letters MNIST, and the result seems to be consistent. And interestingly, the Alex found that there is, so if you look at the social science, so there are different voting sort of models, and one of the voting models is called Penrose square root voting models. So the idea is that in many situations, we consider that the majority, so we make decision based on the majority, 50 plus 1, right? In that Penrose square root system, he's talking about the qualified majority. So the qualified majority is when the threshold between those voting for and voting against is square root of the number of voters. And he proved that only in this case, each voter gets the maximum voting power. And interestingly enough, the Tsetlin machine behave exactly like this. So when the threshold is a square root of the half of the clauses, it is probably because we have those voting for and those voting against. So they can't vote for and against at any time. So there is half of them for and half of them voting against. So, but this rule resembles this Penrose square root voting system. And by the way, European societies, they use this voting system or this qualified majority in some cases. And if the UK followed that particular rule, the rule of the square root, the Brexit wouldn't have happened because the majority was like, it was 52 against 48. So it's not a qualified majority, yeah? So if it's not a qualified majority, it wise not to make any decision rather than to follow this as the simple majority. So interesting enough, and as I said, it seems to repeat itself. It doesn't matter which data set we will use. So the learning sensitivity S is the more difficult case. So apparently it follows the logarithmic dependency. And we found that, again, there are other people studying crowd dynamics. And then in the crowd dynamics, it is widely accepted. So it is widely accepted that there is a logarithmic dependency between the crowd density and the crowd velocity. So we assume that the pedestrian can move with the velocity of the 500 kilometers per hour. But if the crowd becomes dense, so the overall speed drops as a logarithm of the density. And interestingly enough, this particular law was reassembled in our experiments. So, and it's quite natural because the Tsetlin machine, the background of the Tsetlin machine is a collective behavior of a learning automaton. So the collective behavior means that they learn and then to, so the idea that if you want to keep the optimal learning for all of the automatons, you need to increase the learning speed as a logarithm of the number of learners. So it was also interesting resemblance which we can find in a different scientific domains. One coming from the social science, one coming from these people studying crowd dynamics. So this right, and regarding C, as I said, or regarding S, as I said, we found that it is a logarithmic dependence, but the exact equation sort of, it's quite difficult to find. But what we found is there are two coefficients that influence the optimal S. The first one, it depends on the intersimilarity between or within the class and intersimilarity between classes. So the idea is that if you have a very similar data set within the class, the S could be smaller. So because samples within the class are quite the same, so there is no large variation between them, so the S could be smaller. But in the if you have higher similarity between classes, it means that classes are quite similar to each other, like number 5 and number 6, yeah, or like 3 and 9. So between these classes, there is a high similarity. And in this case, you need to increase learning sensitivity to find some fine-grained details of the patterns of the classes which belong to classes which are quite similar to each other. So two factors and the logarithmic dependency. And fortunately, we'll be able to find what is optimal for S as well. It was also interesting observation that we discovered. And we at some point we noticed that if you set T and S in a badly wrong way, instead of getting increasing accuracy, the more you train system, the worse accuracy is. And we call this phenomenon as a dislearning. And this learning seems to be different nature from the overfitting that we can experience in the artificial neural networks. So there are some explanations for this. when you set the too high threshold, it means that it's quite difficult for the Tsetlin machine to achieve this threshold. And if it is more difficult, if it can achieve the threshold, it continue to update Tsetlin automatons, right? On the other side, if the high T is accompanied by the high S with a high learning sensitivity, and the high S, it's allowed to increase more or to include more. Well, it's stimulate includes mostly. Yeah, so you include more and more literals into your clause, and as a result, the clause become really bulky and fragile, because even one single zero nullifies the whole clause. So it becomes even more difficult to achieve the threshold, right? So it's like an escalating escalator. So the high T and the high S, as a result, you are dislearning. And from epoch to epoch, your results become worse and worse. So we call this, as I said, we call this a dislearning, and then for different clauses, you can identify different dislearning domain. And this is useful in the sense that not only to avoid a situation when your accuracy is degraded, but also to reduce a search for your, or to reduce a search space if you're trying to find the optimal TNS. Right. The next story is what is the optimal number of states for the Tsetlin automaton. And well, here we are talking about the small n, because small n, it is widely used in the software implementation where it is n bits, which, so the total number of states is the 2 in power of n. And here you can see that actually we couldn't find the optimal number of n. So if n is too small, yes, your accuracy can't be high. But if you increase the number of states beyond a certain level, you have no gain in accuracy, but the training time increases dramatically, right? So we can see that, yes, there is a good enough number of states. And in our experiments, and also it's interesting that if you have more clauses, you can have less, so you can allow you have to have less number of Tsetlin automaton states. And based on our observation, so for example, the optimal numbers is 6 if you have more than 500 clauses, and 7 if you have in between 20 and 500, and 8 if you have less than 20 clauses. So it's quite interesting. And if you're trying to increase number of states above the values, you won't achieve any gain in accuracy. Only what you could see is only the increased training time. And also interesting that the optimal n actually doesn't depend on the TNS optimality. And if TNS are wrongly set, so you can't compensate it using a larger or smaller number of states of the Tsetlin automaton. And the last parameter that we investigated, it is a number of is there is an optimal number for the training epoch. And what we found actually that there is no such an optimum. The more it's always beneficial to train for longer. So if you have resources, if you have time, train for longer, and then you achieve the better accuracy. However, at some point, your gain in accuracy become very sporadic and incremental. But also what we noticed that there is a different threshold between the number of clauses and a number of training epoch. So potentially, a Tsetlin machine with a favor number of clauses can achieve the same accuracy if it is trained for longer. The only you need to notice that the while scale is logarithmic. So, for example, if you can achieve the same accuracy if you double the number of clauses, or if you multiply the number of training epoch by, or if you increase like a 20-fold or 10-fold with the number of training epoch. So it's like a trade-off, but it's interesting because if you consider ANN, artificial neural network, the Tsetlin machine can be trained much faster than ANN. And sometimes if you don't have enough hardware resources to allocate a large number of clauses, but you have time to train for longer, you can achieve pretty the same accuracy. So that was quite amazing. And then this particular graph explains you what sort of accuracy you can achieve by increasing number of clauses or by increasing number of the training epoch. Right. Time to come to a summary. So in this work, we try to cover all of the main hyperparameters that you need to train. The number of clauses, the TNS, the threshold, and the learning sensitivity, the number of training epoch, and the number of states of the Tsetlin automaton. So the results are summarized here. The most important is that there is no optimal value for number of clauses. If you set TNS optimally, so the more clauses you have, the higher accuracy you can receive. So it's a matter of your hardware resources. So how many or how much of the hardware resource do you have? Then TNS are critical, and TNS are the most important hyperparameters for the Tsetlin machine. And our suggestion for you guys is that set T as a square root of the number of clauses, of the half of the number of clauses. So this is a good starting point, and then play around this number. For the S, it is a bit more difficult. S usually is lower than T, and S follows the logarithmic dependency on the number of clauses. And as I say, there are two factors. So what we need to do, or what we are trying to do now, is to we found that the interclass and interclass similarity is important to define the optimal S. So we are now trying to find what are the measures that can be used to define or to describe this quickly, this inter and interclass similarity, to find the optimal learning sensitivity. Well, for N, well, 8 is good enough. It means that 256 states divided by 2, because 125 is for exclude, 128 for include, so it's good enough. But something in between 6 and 8 is a good number. And for C, the longer you train, the higher accuracy you receive. But after some rapid growth of the in the accuracy, you sort of you stabilize, and then the accuracy again become only incremental and quite sporadic. And well, this is it. So thank you for your attention. And then if you have questions.
Very unique explorations in the first of its kind. One question. So we have time for one question. Okay, so I'll probably start from that question. So you optimize with respect to accuracy, right? So you're looking, how about the different parameters like precision, recall? I understand that accuracy is not always best thing, so you may want to be a little bit more selective or specific. Have you tried to take a look at that? Do you expect any changes in that?
Well, we look at them at some point, right? But for that particular research, we use sort of aggregated metric as an accuracy in general. But it probably is depending on the task that you need to solve, whether to reduce false positive or reduce sort of or increase the true positive. It's probably there is some change could be in that. But general rules is like this: threshold, square root of the half of the number of clauses, and S should be algorithmic slightly less than T. Yeah.
And also, as you explore the number of clauses, you should take into account the explainability. There should be some kind of trade-off there. You say the more the better with respect to highest accuracy, right? But then tractability will be degraded.
Absolutely, yeah. But for the explainability, it's also interesting that when you have a more number of clauses, somehow you need to aggregate them, to provide the rule. Right. Because, for example, you have 1,000 of clauses. You can, so it could be 1,000 of rules, but some of them repeat itself. So some of them become more common, some of them less common. So somehow we need another tool to aggregate those clauses and provide some, squeezed sort of ruling system.
Excellent, very unique exploration. So thank you.
There is an online question from Ola Christopher Granmo. Fascinating analysis and findings, Anatoly. Very interesting and useful. Did you observe any striking difference between Fashion MNIST and MNIST? And have you tried any NLP tasks?
Well, so as I said, this particular work was done on the digital MNIST. But so far, we've done experiments, the same experiments on the Fashion MNIST and the latest MNIST, So we try to cover all of the MNIST datasets. And what we found that T is consistent across this dataset, So the t, with the t, you can be absolutely sure that the square root of the half of the clauses is a good number for you to set. S is a difficult case. What we notice that, for example, if you look at the fashion MNIST, so the fashion MNIST, the similarity within classes are quite low, and the similarity in between classes are also quite large. Because there are, for example, there are shorts, t-shirts, jumpers, which looks pretty much the same. Yeah, so the only difference is sleeves and some of the necks. So when, and for the fashion MNIST data set, the S should be higher, because it become more difficult to distinguish between some classes. So you need to find some very fine-grained differences between the classes. In this case, you need to increase S, right? So if the similarity within the class is high and similarity between classes is low, you're going to use a low S.
Shall we allow it, or we just push to offline discussion?
Maybe we can take some of these questions
in the bus.
Your technical socials, and I'm going to have to make some announcements before we head to the bus, and we may want to conclude this session, please. Thank you.
All right.
Thank you.
Thanks a lot.